Hello, Paul Russo here to walk you through the use of our nifty SMALS apparatus here at Opal. SMALS means simultaneous multi-angle light scattering, and the instrument is rare because it's a multi-angle and a multi-correlator device. It's built around a Wyatt Dawn EOS, following designs first worked out by Grigor Banchev and later revised by Shujun Zhang. An important feature of the SMALS apparatus is that it requires no laser safety training. Unlike our other DLS instruments, which also can do SLS, the embedded laser in the SMALS apparatus is self-contained, so it's quite safe to use. The SMALS instrument can record DLS and SLS signals using 8 APD detectors, avalanche photodiode detectors, plus another 8 simple diode detectors. Altogether then, there are 8 channels of DLS and 16 channels of SLS. Today we're just going to work on the DLS side. We're just going to illustrate the DLS side. But first I want to say a little bit about why multi-angle matters in DLS. In our tutorial review articles, which are sort of locally known as Chapter 12 and Chapter 13, of a book edited by Jimmy Mays and Imran Malik. The guiding principle of dynamic light scattering is described as follows. Basically, if it moves, DLS can see it, or at least there's a hope that it can see it. It has to actually produce some change in the scattered field of light when the motion occurs. But all kinds of motion can be detected. So usually we focus on translational motion. So for example, if I have a simple spherical object and it moves from point A to point B, that's what we can detect. But if I have a rod-like object, the rotation of the rod can also sometimes be detected. The key thing is that the rod has to be sort of a certain large enough size to measure. Okay, so that rotational motion adds a contribution to the correlation function, which becomes increasingly easy to detect at high scattering angles. Another important reason, even if you're looking at spherical objects, especially if they're large, is that you may have objects of different size. And if there are mixtures of differently sized scatterers, the large ones scatter much more strongly to low angles than they do to high angles. So if you measure at a fixed angle, most fixed angle instruments have a 90-degree scattering option, you may find that the large objects scatter very weakly to them, and you're sort of focused only on the small ones, and you don't even know that's a problem unless you do multi-angle light scattering. So today we're going to illustrate with some samples that have both of those problems. They have a rod-like shape and they are different in size. And we're going to be looking at cellulose nano crystals, which are kind of a lot of fun to study. And what we'll see is that the apparent size really depends on scattering angle. And that's obviously got to be considered. If we were to measure these samples at a single angle, we would certainly get the wrong answer. Okay, so doing multi-angle DLS measurements used to be a tedious process, and in most places it still is, because most instruments measure at only one angle, or if they do measure at multiple angles, they only do it at one angle at a time. You have to manually or maybe use a motorized detector arm to change the angle, and that requires a lot of extra time. What you'll see here is that we can measure all the angles quickly. Do bear in mind that the static light scattering signals are also recorded by the apparatus. We're just not focusing on those today, but that's actually an interesting thing to do. After the data are gathered, we're going to drop them into an Excel spreadsheet. This too is a pretty fast process, and it's just the beginning of the analysis, but at least we can get you'll see that we can get the data out and into some manageable form like Excel very simply. So what I'm going to do now is operate the instrument and walk you through a little tour of it. This is how it looks. And what you'll see is that there are 8 detectors. 1, 2, 3, 4, 5, 6, 7, 8 detectors. They're color coded. The lowest one is on the left and the other 7 are on the right. The color codes are matched what's on the ALV. They all turned on by these detectors here. The ALV software has plots them in different colors and in different representations. Here we're looking at the semi-log plot, and now I've started the device to run. And what you'll see over here in this trace on the right panel, you'll see that the intensities are being traced out. And you'll notice that the lowest scattering angle, which is in a bright green, seems to have larger fluctuations. And that's a little bit deceptive. They are larger because the intensities on the ALV software are gathered at 400 millisecond time intervals. At the higher scattering angles, the intensities have gone up and down many times, and so it sort of averages out. The correlator is recording those up and down intensity fluctuations properly. It's just that you can't see them. It doesn't display on this on this time scale where they only show you every 400 milliseconds. So it's almost done running. It's a simple minute run, and then after it's done, we're going to go click and do what we shouldn't do. We're going to run content analysis very quickly, and the system will also, when we save it, do its own automated cumulant analysis. Okay, so now we have collected some data on the SMALS device, and we've stored it in a directory, a folder. In this case, it's got the name that you see there, AA1 to 20 dilute.asc, and there should be a README file for the data. So it, this one is just designed to test this notebook. It happens to be some cellulose nanocrystals, and that's a system that's rod-like and polydisperse. So we don't expect linear gamma versus q-square plots out of this. It's a kind of a good reason to have the SMALS device with its multi-angle, multi-correlator technology. Let me show you how we can get the data into some plots. So what I'm going to do is close that, and on the desktop there will be a folder that has some templates in it. And the one that we want is gather ALV QMU and 1 exponential G2 with macro. And I'm going to take the version copy. We want to be careful about never destroying these, so we keep a copy. I'm going to drop that into my directory here. And you can rename it if you want to, but I think it's good to just let the directory have the name. In this case, temp test. And so now we have everything that we need. Let's go ahead and look at what these ALV output files look like. This is from a single run, is one of the things that it says right away, is single run data. And it has some header information. The angle information is all there, and these should be your angles. In the instrument as it's currently configured anyway. Wavelength, temperature, all that's there. Some intensity data are there. And finally there begins the correlation function. The first column of this correlation function, first column, is your lag times. And then we have 8 channels representing our 8 detectors. I guess I needed to drag one more. So that's 7, 8. And then we have 4 channels of zeros because the correlator is really designed for 12 channels and we only have 8. So what I'm going to do is take these data and just drop them into an Excel program, and we'll see how that works. Let me close this for the moment and then come back to it in a minute. Let's look at the Excel worksheet to gather ALV, CUMU, and exponential data. Oh, it can't open at the same time, so it's already open. That's okay. Close that. It was already open. The first thing I want to do is enable content. It has a macro in it. And let's explore what it says. There are some instructions about using it, so you can read that if you want. There is a worksheet called Data Drop, and you see that it's not populated, and it has some plots there that will appear once we do populate it. Then it has another spreadsheet called Main, and in this spreadsheet are data that it fetches from the data drop worksheet once we drop some data there. Right now, what you should see is a whole bunch of ones here in all of these things. So this column here should all be ones. If you happen to drop in a previously used worksheet, you can set all of those to ones using a macro. And to do that, you can go to Developer, Macros, and you'll see Set Data to Ones for a template, and you can just run that. We'll run it. It won't hurt anything now. And now this spreadsheet has been reset, and so if it did have something in it, you can kind of reset it that way. It's a convenient worksheet, but it's kind of long and in the X direction here. And right now you'll see some plots. And the plots that it will generate for us are cumulant data and cumulant 2 data, cumulant 3 data, and then it will get mu2 over gamma bar squared parameters. It also will generate for us 1 exponential D2 data if we have dropped that in, if we've done that analysis. The data set we're dealing with today is just not really appropriate for that, so I don't have that. But I'm going to show you where you would drop it anyway. It will get it for you. Put your data right here. When you run the ALV 1 exponential G2 analysis, you can copy the data, and it will give you just those 3 numbers: an amplitude, a decay rate, and a baseline. And you just drop them 1 angle at a time into these spaces, 1 for each angle. The color code here is the same color code that you have on the ALV screen, and it's the same color code that we use throughout the SMALS system. Okay, so now we're ready. This is open. Let me go and open that ASC data file. ASC means ASCII. It's ASCII text data. And all you're going to do is just position your cursor right where it is, just leave it where it is, and hit Control A to select everything. And I'll hit Control C to copy everything. And then I'll Alt Tab over to the Excel spreadsheet and the Data Drop spreadsheet. And this is where we're going to drop it, in this slightly darker green cell, and just hit Control V to drop the data there, and it'll give you a warning which you can ignore, and then it will populate these plots, and that will remind you of what you should already know about the data from watching the SMALS data acquisition. You should already have seen these plots, but it's nice just to have that reminder. Now if we go over to Main, we should see that it has updated everything. Once we click this macro button. Here we go. Click that button, and now the data have been put where they belong, and all the plots are present. Well, as advertised, this is a data set. Let's look at this one down here, which doesn't have a line drawn through it yet. And you can see even for the third cumulant that this is very curvaceous looking gamma versus q-square plot, and that's because of the polydispersity effects and the rod-like shape. And you can then divide gamma by q squared to get your d-app versus q squared plot, and you see, oh my god, that's not flat. There's a definite correlation there. My hydrodynamic radius correspondingly will decrease, so you can use these data, try to make some sort of extrapolation to 0q to get the best estimate you can out of cumulants data for these hydrodynamic radius, if that's what you want. You probably want to go ahead in this case and do a content style analysis, a Laplace inversion analysis. And we know that because if you look at the mu2 over gamma bar squared plot versus q squared, we see that the overall value is well above the 0.3 threshold. We sort of look at 0.3 as where it becomes sort of plausible to make good content inverse Laplace transform plots. That's nothing magic about that number. That's just based on long experience. And what you see from the trend here, there's a slight upward trend. I don't know if that droop there is to be regarded as realistic or not. But if we did believe in this upward trend, it would be telling us that the data are getting somewhat more non-exponential high angles, which would suggest that we're starting to pick up the end-over-end tumbling of the rods. That's the sort of thing that will lead to a rise in this mu2 over gamma bar squared parameter. A decline in that would indicate polydispersity, and we're seeing polydispersity of things that are large enough to scatter weakly to high angles. So in this case, you have both effects going on. It's a little bit hard to sort that out, and really can't do too much about that. But anyway, you have all your plots, and what you can do now is export these plots to something nice like Origin and make pretty plots and do better fits. And this is really intended just to analyze and to sort of simplify the gathering of the data from the 8 channels all in one step. So I should have pointed out earlier that there are parameters. Normally they'll be set to the right wavelength for this instrument, and you have to adjust the temperature and the viscosity and the refractive index. So that's basically it. And the only last thing to do is hit save when you're done. Then it gets a warning about compatibility. Just ignore that and close it. And we're done.